Hello, how are you guys? Let's start our session on generative adversarial network. So today I am basically explaining you the generative adversarial network architecture and how to train this model and how to pass your custom data set. So let's start and welcome to everyone guys in Deep Learning Narendra Singh Dangi channel. Okay, so where is the material? YK. Okay, so this is our generative adversarial network. Looks like. Mhm. Yeah. So let's see what is the meaning of generative adversarial network. So generative means generate data, create fake data, and adversarial means generator and discriminator each competing to win, and network basically architecture. Yeah, so let's explain each term in a depth. So generative basically means we have to generate data, create fake data. So how to create this fake data? So basically in our neural network architecture, we have to define a latent space. So here basically firstly we have to generate randomly different numbers, and this latent vector will be passed over our neural network. Basically we have some architecture there, so we have to pass this latent vector to our network, and then we have to say to create a three-dimensional image or Bundy image, so that we can Bundy image basically means mm, black and white image, and 3D image means basically RGB, that is green blue image, colored image or basically. So we have to define this architecture so that this will be able to generate like that image. So that's just for generative. Generative means basically we have to generate a latent vector basically. And adversarial, what is adversarial? So adversarial means basically they are fighting each other. Basically we have to create two models, one is generator and one is discriminator. So basically both are fighting to each other to, like, generator is trying to basically minimize the generator loss, and discriminator is trying to minimize the discriminator loss. So basically generator trying to fake and discriminator trying not to be fooled. So what is the aim of generator? So generator basically is aim to generate the image which looks like similar as a real image basically. So, and discriminator is there. Discriminator basically have to discriminate like this is a real or fake. So we have to train until that discriminator will not be able to catch our that error, like it's a real or fake image. So we have to train until that the discriminator loss will be very low. So we want this basically. So by training this both model, we have to get a good model after the some number of box. So basically this is the idea that we have to follow it. So firstly we have to generate this image, and after generating this image we have to pass to the discriminator. So for discriminator we have to pass half image of fake image and half image of real image, so that, and this half of image basically we have to pass to the discriminator. So discriminator now have to basically try to find out like this is a real or fake. So if our discriminator will not able to find out like this is a real or fake, then our aim will be, our goal will be achieved. So that's what we want. And network basically the CNN network, or basically fully connected neural network. We already know this. I think eh, this is basically a transformer. Like basically we can create this model using our TensorFlow library, or a network is there. So now coming to this slide, and here basically what you have to do, firstly this is our latent vector, random noise seed. So basically firstly we have to generate this randomness, or basically a latent vector, or this is basically our hyperparameter dimension vector. So it's basically 1 into 100 vector we can take it, or we can basically hyperparameter, you can take it any value. So basically we can take it as a 100 return vector, 100 dimension return vector, one cross 100 dimension, and then we have to pass to this network. So the generator network is there. So basically this network will create a fake image of this by passing at this latent vector. We have to say to this generator model, we have to, I want a image which looks like real image. So that's the work of the generator. And now we have to pass half image of the real image and half image of the generated image by our generator network and pass to this discriminator. And now the discriminator will discriminate like this is a real or fake image. So at the time of training the generator, we have to pause, or we can say that pause this discriminator not to train, and at the time of training the discriminator we have to pause this generator. So basically this is basically a sequential training of this model. At the time of training the generator we have to not to train the discriminator, and at the time of training the discriminator we have to pause the training of the generator. That's how this will work. And now basically we have created the half of fake image and half of real image. Now we have to pass both half image of the real image and half image of the fake image to this discriminator. And so at the time of first epoch basically, so the discriminator will know, yeah, basically first epoch we have a random noise. So this is basically able to find out, yeah, this is a real image and this is a fake image. So the our discriminator loss and generator loss is very very high. But after some number of epochs like 100 epochs, the upper we have to train every times like 100 times generator and 100 times discriminator. So both will be very good enough to discriminate each other. So we have to train until that our discriminator like generator loss is minimum as possible as compared to discriminator. So we have to train until that our generator will be full to discriminator basically. So generator now will give at the time. Now we have trained until 100 number of epochs. So now our generator will be able to create a similar image which will looks like a real image. So now we have passed to this half image of real image and half image of the generated image by generator our, and then we will pass to a discriminator. Now discriminator will not able to find out like this is a real image or a fake image. So that's we want only. So if our discriminator will not able to find out like this is a real or a fake image, our goal will be achieved. That's how we have to train it. And both we have to calculate the generator loss and discriminator loss, and we will pass to the second epoch, so that basically we have to minimize this both of the loss. That's how this works. Five steps of generative adversarial network. So in the first step, basically define generative adversarial network architecture based on the application. So based on our problem statement, we have to define the generative adversarial network architecture. Train discriminator to distinguish real versus fake data. So we have to train our discriminator model to distinguish, basically to classify this is a real image or fake image. And now we will train the generator to fake data that can fool the discriminator. So in the third step, basically we have to train the generator. So we basically want to train the generator so that this generator basically can fool our discriminator. So fool means basically our discriminator will not be able to find out like this is a real or fake image. We have to create that similar image like a real image. Continue discriminator and generator training for multiple epochs. So basically we have to define this number of epochs, and until this number of epochs we have to train our discriminator and generator each in a sequential manner. Shape generator model to create new realistic fake data. Yeah, so after this training of this discriminator or generator, we have to shape our generator this new generator model, and then we have to create a new realistic fake image. Now, application of generate fake data for argumentation and other medical machine learning algorithms. Yeah, so using a generative medicine, we can also augmenting like we can generate fake data basically that will looks like a real data. Generate face, basically if you go to this website like this person does not exist.com, then you are able to find out like here every time if you will refresh this page, you will get a different person image, and basically this person does not exist in the world. This faces will be randomly created by AI. You can see that. You will try to, you will get enjoy. Image to image translation, you can do it. Text to image also do it. Like here you can see Delhi. Using a Delhi, you can use convert your text to image. So for resolution, you can do it. Domain transfer, LM to EM. Also, you can do it. Mhm. Yeah, so that's it for this, guys. Now coming to our coding part, like how to implement this solution to generate, how to create your own generative adversarial network model. So our aim is now to convert this image into this image. So we have to remove all of these things like blurry image, like we have to remove this and convert this type of image. So using a generative adversarial network, like using a domain transfer, basically we can convert this image to this image. So we have to train our model. So data, now we have a data set which contain 30 images only now. So what I have to do? So this is the our generative adversarial network. We can see that we have a random noise. Basically this random noise is known as latent vector. Using a generator, we have to generate a sample data which will looks like our real images. We have some number of real images, and now suppose we have a 30 number of real images. So then we have to pass 15, randomly select 15 images from there and create 15 images from there randomly, and then we have to pass this image to our discriminator. So now discriminator will basically discriminate, like discriminator is basically a classification algorithm. So here we have to classify like this is a real image or a fake image. So now after discriminator, we will get some loss like discriminator loss or generator loss. So now we will get some loss. So we have to, in the second epoch, we have to minimize these losses. So again we have to train this number of times, so we will get a good generator which will able to fool to discriminator, so that which will able to fool our discriminator. Like this is how good is how, like this is be able to create a image which will looks like real images. That's we want it only. That's how it will work. So by training this generator and discriminator every time, we will get a good model of a generator. So let's see how to build it. So to build it, basically we have used some library like NumPy, Panda, CV2, Matplotlib, Globe, TensorFlow. Basically NumPy, Panda, everybody known as CV2 also, like computer vision. This is, and Globe is there. TensorFlow. TensorFlow is basically very good library if you will using this. So TensorFlow will contain of many models, and Globe is to read the dataset, and Matplotlib to read the, like display the images, and CV2 for computer vision or OpenCV we can say. Now, so what I have to do? Load our image data. So using a Globe, I have load this data, and labels also I have load. Now I have visualized this image. So basically we have to convert this type of images into this type of images. That's our aim. So now what I have to do? We have to split it and convert into a same number. Now this is our generator. So here basically what we have to do? Pass this photo and label. So that basically generator is to generate the data set. Basically generator. So here we have to define our generator. So basically here we have passed our photo and label. So we say that every label of item basically and photo, we have a x and y. So we will get this our photos. Now coming to the model building, taking reference from is to part translation with conditional adversarial network research paper. So now we have to define our discriminator model, and below we can define our generator model. Basically this is not a generator model, basically this is a generator. Generator means basically we are generating this image only, not a generator model, not about discriminator model, how this will looks like. So in discriminator, what we have to do, we have to pass these images basically. And discriminator is basically nothing but basically a binary classification model of a CNN. So in this basically we have to pass image shape. So now we have to pass image shape and initialize our random normal with a standard deviation 0.02. This is basically hyperparameter, you can change it. And image, input image. So for input image basically we will pass this to this our input. And what is input? Input is any model, I think. Not a model, basically input is basically we say that input image with a shape of this, basically we will pass some shape, so that we say that our input shape will be this much for input and labels for this shape is also. Now we have to merge this input shape and the label shape. So now we have a merged model. So we have a image of our this like input images, and then we have to define our convolution to delay with a 64 like a CNN basically. We can say this is our hyperparameter with 64 number of frames, or we can say a number of parameters. Basically this is known as CNN layer basically. And this is 4 by 4 cross. Basically we have to apply stride. Stage is 2 cross 2 basically we have applied, and 4 cross 4 basically, and this is known as mm, our grid box. So basically we have to apply this to our convolution 2D layer. 64 number of what can say convolution 2D. So here we have to define, like we have to create 64 number of different layers and 4 by 4, basically 4 by 4 shape of. And start we have to apply 2 by 2, and padding is same we have to apply. And kernel initializer basically init basically means a random normal with a standard deviation 2. And basically we have applied this on our merged this image. And then we have to apply leaky radio activation function, and with a alpha basically this is a hyperparameter. I think you have already seen my deep learning framework, deep learning playlist, so I think you will know that. And again we have to apply convolution 2D layer with 128 frames and 4 by 4 cross. This known as our, I don't remember that name, like pixels with 2 by 4 by 4 cross. Basically we apply start 2, and we have applied, we have defined this our CNN architecture. And after basically we have applied a one output layer with a activation function as a sigmoid. So sigmoid basically use a binary classification algorithm. So basically you have to apply, if we are using a binary classification algorithm, then we have to apply a sigmoid activation function as a output layer. And the loss basically we have applied a binary cross entropy loss. And this is our Adam optimizer with a learning rate, and you can see a beta equal to 0.5. we have we have to apply this Adam optimizers and activation function as a leaky value. You can also apply a value activation function, but leaky value is applied. Basically this is a hyperparameter, you can change it. And optimizers is applied loss weight. So that's our discriminator model. If you pass this image to half of this real image and half of the label image, basically here we have to pass half of the input image and half of the real image, like fake image and generated image. So basically now, so by passing this basically we have this discriminator will describe like this is a real or fake image. That's how this will work. Now coming to our encoder block and a decoder block. So basically in generator I have applied a unit architecture model. So here firstly we have to apply, like here we can see that this is our generator, define generator model. So here if you pass a 256 256 cross 3 image, then this will be converted into some like 1 into 1 into some number of basically pixels is not, basically we can say a number of layers, what we will say, I don't remember the exact name, like 1 cross 1 cross, or like if you pass then 256 256 cross 3 images is there, then this are the number of different channels is there, like. So at the time we have to pass 256 256 cross 3 image, then this will be converted into 250 like 126 into some, here we have to define 120, so this will be converted to 128 different channels. So that's how this will work. The define encoder block. So firstly we have to encode this image to a latent vector, and then we have to again get by, we have to, now we have a latent vector is that, then we have to again, firstly we have to encode this image, and then we have to again get a good image like by 256 256 cross 3. So firstly we have to encode this image into a latent vector, and then we have to again decode this image from encoding like data and vector to our good image basically, or basically using a decoder block we can again get this real image. So what we have to do in this model, firstly we have to pass like a image like this and to our unit architecture model to like this, and then we have to convert this image into a latent vector of 100 dimension, and then we have to again get this vector from again a decoder, using a decoder we can using by passing this latent vector we can get this type of image using a unit architecture. So that's how this will work. So firstly we have to encode our image, and then we have to decode our image. So by passing this will work. So like now see how encoder will work, how to create an encoder. So encoder basically are block basically. Here basically we have number of filters. Yeah, this is known as number of filters. So basically number of filters we have to pass, and this is basically number of layers, number of filters, and 4 cross 4 basically these are stride, and this is this, and here batch normalization is also applied, and leaky value activation function we have applied. Layer in, and the number of filters, batch normalization is true if the batch normalization is doing. And in decoder basically we have to pass our skip connection is also applied. If basically skip connection is help us to minimize this basically dead neuron problem, or we can say a mm, vanishing gradient problem. To remove the vanishing gradient problem, we have to apply skip connection, so that our connection will be established between the same layer, so that if our model will be trained in a good manner. So that's how this will work. And also we have applied some dropout layer to not to like to avoid the overfitting. That's the decoder block. Decoder block is same as encoder. In encoder basically we have to reduce the dimension from higher dimension to a lower dimension, but in decoder basically we have to again get the same dimension. So basically here we have to uh, expand our image from lower dimension to higher dimension. So basically first we have to decode this, encode this image, and then we have to decode this image, and then we will get a image. So basically we have applied a 10x activation function. So 10x activation function ranges from -1 to 1. So we have to convert our input image into a -1 to 1 vector. So basically we will convert it into using some formula, we can see it after some time. So that's how this will work. Now we have to define our generator. Full, basically this is our model, whole model basically. Yeah. So define generator. So in generator we have to find generator model and discriminator model and image ka shape basically. So by for layer in dimension dot layer basically we have to pass it our image basically pass, and every image will is firstly passed to this our generator model, and then we have to pass this discriminator model. So here we have to pass our input image, or basically input src, basically known as input image. So this input image basically firstly go to generator model. So firstly we have to train our generator model. So at the time of training this generator model, discriminator is constant, and now we will get generator output, and then we have to train our discriminator model. So at the time of training the discriminator model, so in discriminator model we have to pass half image of our real image and half of the our generated by fake model. So basically here we have to generating this image by passing this input image, and then we have to generate some new different image, and then we have to pass this to our discriminator model. And discriminator basically will give you some like loss. So basically how many like discriminator loss, basically discriminator is defined to like how many I am getting the correctly and how I am getting incorrect model. So that's how this will work, and here we have to define our models. And model basically input images basically pass, and discriminator output and generator output basically we have to pass it. And Adam optimizer is also applied, and binary cross entropy MAE loss function is applied. Optimizer is Adam optimizer. Loss bit metric accuracy basically applied to seeing like how our model is giving the accuracy. To see the accuracy basically we apply pass the matrix SI accuracy. So that's how it will work. Now generate, this is our whole model. Now to see like how to generate real images, how to generate real samples. So basically we have a data set. Basically in our data set we have to take it half of these images. So basically train A train B equal to data set, and in that basically x1 x2 train I, basically we have to ix basically random integer, basically we have to take it random integer. And this and random integer, basically using a random integer basically we will take this image, and basically we have applied a bunch. So basically we are give output to generated image as a bunch. So like by this basically we say this if this is a image, then this is a label as a bunch. So this means this is a real image. But in fake image basically we have to generate firstly using a generator dot predict function. We have to generate a fake image. So at the initial stage this will randomly generate a noise basically, and basically we define as a output as a like or label as a 0 to this image. And so for this is the use of generator fake sample. So that's how will we generate this fake sample. Now generator loss and accuracy we have to define it, and now we have to calculate it. So here we have to train this model. For training this model we have to define a the model. So for training this basically we have passed the discriminator model, generator model, GAN model. This is our whole model and our data set and number of works, like how many number of works we want to train it, and like batch size. So basically we have defined the batch size of 1 because we have a small data set, only 30 images. So that's why I have defined it sub 1. So now we have to again take a data set, and now we have to like batch per epoch. So basically number of batch epoch. So basically this will be train it into a number of 30 times, like number of images times. So basically for every epoch we have to train 30 times. Basically we have defined a number of batch equal to 1. So that's why. So we will basically we will get some discriminator loss 1, loss 2, train on batch basically real image and real B and real A fake B, basically that we can get accuracy. Then image dot step is defined, like now we have to see in a model like how this will so see. So basically in discriminator we will pass half images of our real image and half images for fake image, and then this will be combined, and basically this will be concatenated, and then we have to find like output as a one. So here we can say that this is our real image or fake image. Using this architecture we can find it out. And this is our generator model architecture. You can see that this is the very good architecture. You can see that Firstly we have to pass it out like 512 cross 3 dimension of image, and then we have to using our encoder we have to encode this image to a 1 cross 1, or basically here we can see we have to encode this into 4 cross 4 cross 512 dimension, and then again we have to apply a decoder. So using a decoder we will again get a same image like 512 cross 3 dimension of image. And here you can see these connection are there, so these connection are known as skip connection, and this skip connection help us to overcome the bouncing gradient problem and exploding gradient problem. That's why we have to apply this skip connections. And now we have a pre-processed data, and we have to here we have to convert this image our image into -1 to 1, because we have applied a 10h activation function in the output layer as a here we have to apply our here activation function we have to apply a 10h, so that's why this will give us a images of -1 to 1 pixel, so that's why we have to apply it. Here we can see that this is a source image, this is a predicted image, and this is our actual image after training number of epochs. As like I have trained many number of like 1499, so 1499 means basically we divided by 30, so by 30 epochs basically we will get like I have trained this 50 number of epochs. And this how you can see that like how they are looks like, basically this are look like similar images. That's how it will work. That's it for today guys. Here you can also see that like matrix performance. Firstly, like starting number of blocks, the accuracy is very low, but after training the like some number of epochs we will get a good accuracy like 0.7 approx, like 70% of accuracy we will get. These are generator loss. Firstly, the generator loss is very high. After training some number of epochs like 50 number of epochs we will get a very low generator loss. And that's how this will work. Thank you guys for today. I have explained the generator with adversarial network architecture. Basically, this is very good architecture. If you want to do some mm, model architecture or build something in images, this generative adversarial network will works very well. So if you want to also do a background remove from an image, suppose you have got some like 50 number of images, and here we have like suppose you want to remove background from this image, so we have to train this model like if we pass this then I want out this. So you can also remove background from this images using to train your model like using a generative adversarial network. That's how this will work. So one time all again I have to explain like listen very carefully. So firstly basically in that basically we have to pass some latent vector, and this latent vector basically to generate our real fake image which will looks like basically our aim is to generate a fake image which will looks like a real image, and then we have to pass this image to our discriminator. So this discriminator will help us to like find out this is a real image or fake image. So basically the aim of a generator is to fool the discriminator, and so by doing again and again and again the generator will be trained so that the discriminator will be fooled. So basically we want something like that, like that discriminator will not be able to know that like this is a real image or fake image. Basically we want this. But in the current project basically what we have done, basically we have passed this image here. Basically we have convert our image real image to a firstly here also using a generator network. Firstly apply basically there is a different type of generator network. So basically here I have applied a unit architecture. So in unit architecture basically we have to pass our real image, and then this real image basically convert into a latent vector, and then again we have to get a use this latent vector to generate a real image like fake image. So basically our aim is to create a fake image basically which looks like a labels. We have a labels now, so basically we say that this labels basically known as our real images. So passing this new image basically we will get some latent vector, and using a latent vector we can again get a this image which looks like our labels, and then we have to pass this our discriminator or to set discriminator this is a real or fake. So by passing again and again we can get a as minimum as possible generator loss so that our generator will be trained. That's how this will work. Thank you guys. I think I have explained generative adversarial network in a very good manner. Let's meet in the next lecture tomorrow. Generative adversarial network is over now. Thank you guys. Jai Hind, Jai Bharat. Please subscribe my channel.